Yeah, so welcome everyone for this IA's Astrophysics seminar series in person as well as those who have joined online. And our today's speaker is Dr. Avinash Surendran. He is presently KAPA postdoctoral fellow at Keck Observatory in Hawaii. Dr. Avinash obtained his master's and PhD degree in astronomical instrumentation from IA's CU MTech PhD program here at IA. From 2010 till February 2018, and during which he has designed two astronomy instruments. The first instrument was a LUNA's scintillometer, which could derive the nature of ground-level atmospheric turbulence from the minute fluctuations in the moonlight due to the turbulence. As well as he designed another instrument called SPARC, which is a scalable platform for adaptive optics, real-time control. This was aimed at testing the feasibility of using FPGAs as computing platform for real-time sensing and correction of atmospheric turbulence. So after his PhD, he was at IUCAA as a postdoctoral fellow in 2018-19, and from 2019 onwards, he is at Keck Observatory as a KAPA fellow, which is called Keck All Precision Adaptive Optics Postdoctoral Fellowship. And he is in Hawaii presently, visiting IA, and he is proficient in the field of electronics and is having high-level working experience in digital system designs, including FPGAs, VHDL programming, and hardware interfaces required in adaptive optics. He is also having expertise in performing different types of simulations and statistical data analysis. And his main interest is in adaptive optics, exoplanets, real-time control systems, and FPGA. He is a recipient of IA's Best Instrumentation Paper Award. Today he is visiting us and we'll be talking about daytime calibration and algorithm development for Keck All Precision Adaptive Optics Tomography System. And I'll invite Avinash for giving his talk, but before that I'll just mention that in the next month's issue of Tooth magazine, he's having a very interesting article. So I will recommend that you please read that as well. You get to see or get to know a lot of different things which he has done in his during his time at IA. With that, I request Avinash to present today's talk.
Thank you, Prasanna. It's good to be back at IA after such a long time. We have been going through pretty tough times, but it's good to catch up, travel, get to know one another, meet new people. So this is one of the first travel after the pandemic that me and my wife Preeti has taken outside of Hawaii. And it's a good place to be. It's one of the best places to be here. So yeah, so as Prasanna mentioned, I had been working in the field of adaptive optics during my PhD and for a brief stint at IUCAA immediately after my PhD. And currently I'm working on the Keck All Precision Adaptive Optics System. So I've structured the talk in a way where I'll give again, brief overview of adaptive optics as a context. I know most of you are familiar with how AO works, but as a context for how it fits into the KAPA upgrade. So currently the adaptive optics system at Keck is a very bare basic vanilla AO system, which consists of a single deformable mirror, a single wavefront sensor, and a controller which decides what shape the wavefront corrector should be. So it basically, and again, giving a small introduction, many of you may know it. So a very bare basic high order adaptive optics system consists of a deformable mirror with lots of actuators which can change the shape of the mirror, which is a very, very thin phase sheet, more than 1,000 times a second to compensate for the distorted wavefront coming from the telescope. And then it is, most of the AO systems around the world are in closed loop. What it means is, so it reflects off from the mirror, it comes to a wavefront sensor, and the wavefront sensor is usually an array of lenslets called the Shack-Hartman sensor. This is the most used kind of wavefront sensor in all of AO systems around the world. There is something else called the pyramid sensor also, but it's used in very niche applications. But the Shack-Hartman wavefront sensor essentially consists of large number of lenslets in front of a camera. So instead of creating one image on the camera, you have a two-dimensional array of images of a star on the camera. So if it is a perfectly plain wavefront, all of these spots should be equidistant from each other, and any distortions will lead to deviations from these positions for these spots. So we detect the shape of the wavefront by understanding how much these spots have shifted from their original position if it was a plain parallel wave. So, and as I said, how it works is initially the wavefront is distorted, comes and hits the deformed mirror, then it gets detected by the wavefront sensor, and the controller immediately corrects for the deformable mirror. And so any reflection which comes after that from the deformable mirror will be just the residual. It will not be the whole wavefront. So in the time that it took for it to correct this wavefront corrector, and with the spatial errors that are there on this wavefront corrector, whatever residual error is there only comes to the wavefront sensor. So that allows us to have to design the wavefront sensor in a way so that it can be designed with a low dynamic range in mind. As you can see, if the wavefront distortions are very high, maybe the spot can move from the back of this lens to the next lens, and we could have lots of problems. Right. So what wavelength? So this is happening in the visible wavelength. So because the lasers that we shoot into the sky for creating the laser guide star is usually 589 nanometers. So this system works in the visible, but science is done in JH and K bands. So, and one important thing which I've been working during the PhD and here also is this equation, very simple equation. So what we have is this wavefront sensor actually detects the wavefront slopes. As the slope of this wavefront increases, the deviation of the spot increases. So S is an array of slopes, and phi is the array of voltages that you give this actuators. And you have a many-to-many n by n matrix. So if you have n lenslets and n actuators, you have a matrix called the interaction matrix, which is an n by n matrix, which is used to transform from the wavefront sensor to the wavefront corrector. And this is the one, this matrix multiplication is the one which decides the computational requirement of the adaptive optics system. And larger adaptive optics systems usually need larger number of, larger adaptive optics systems means AO systems for larger telescopes usually have larger number of actuators and larger number of lenslets to accurately spatially sample the wavefront. And because of that, they have a large matrix here, and this matrix multiplication has to happen thousands of times a second to compensate for the atmospheric turbulence. And because of that, the computational requirement runs into a lot of teraflops, which GPUs are currently able to do, FPGAs were able to do much earlier. So this is just an overview of the AO system. So in any AO system for a large telescope, we try to reduce the error budgets. These error budgets are the different contributions which add to the wavefront deformation. Earlier, I showed the distortion of the wavefront coming to the deformable mirror. So if we can, I mean, the whole point of an AO system is to make the wavefront as plain as possible. But I mean, in the ideal world, this works, but in the practical world, there will always be limitations of how good we can correct the wavefront. So this just gives an example of some of the error budgets where, for example, depending on the site, there is a parameter called the Freed parameter. So this Freed parameter actually decides how distorted the wavefront is, and it can vary from site to site depending on the seeing conditions. And the adaptive optics system has to be designed in a way where the lenslets or the deformable mirror actuator pitch has to be of the order of this distance of R0, which is about 10 centimeter on the pupil plane. So, and another error budget is called the Greenwood frequency, where it depends on the wind velocity. If the wind speed increases, the atmospheric turbulence is changing much faster, and you have to correct it at much faster speed. So a combination of the Greenwood frequency and the Freed parameter decides, sorry, this is the coherence time, and the Freed parameter decides the Greenwood frequency, and it changes with wavelength also. So this is how usually an AO system is designed, depending on what wavelength the AO system works at, the Freed parameter, the time delay, the median wind speeds which are there. So this all feeds into the upgrade that we have in KAPA, which is essentially upgrading the AO system to attack each and every error budget to reduce it by 50 nanometers, reduce another 50 nanometer scale, to the point where we can do better science. And yeah, you are mostly aware of this, that one of the main problems in adaptive optics is, as I showed, because we are splitting the light using those lenslets into multiple images on the camera in an AO system, and we are running the adaptive optics system usually at more than 1,000 frames per second, the signal that we get on the camera is very, very small. So in a conventional adaptive optics system which relies on starlight, we are usually, for a 10-meter telescope, it's usually limited to a magnitude 8 or 9 guide star. And we cannot use a star which is far away from the object of interest, the science object of interest, because then we will be sensing for one region of turbulence, and we will be correcting for another, which means that we will not be getting good science images, but at the same time, we'll be seeing very good wavefront information from this side. So this is why we use laser guide stars, where we shoot a sodium laser at a wavelength of 589 nanometers into the mesospheric layer, where there is a thin layer of sodium atoms which get laced, and depending on the power of the laser and several other factors, the molecular intensity of the sodium layer, you can create whatever magnitude of guide star that you want, depending on the AO system that you're using. So this is the AO system at Keck, and the advantages are lower angular anisoplanatism. This is the jargon, this is the word that we use for the error due to the uncommon paths that I've shown here, that you're sensing for one turbulence and you're correcting for the other. And then the second error which we reduce is the lower measurement error. Measurement error is due to the lower signal to noise ratio in the Shack-Hartman wavefront sensor. The camera, if it has a smaller amount of light on the wavefront sensor, the accuracy with which the centroids are computed also reduces. And that adds to the error in the measurement of the centroids itself. And but the problem here is, which KAPA mainly addresses, is something called focal anisoplanatism, where so what happens is here you can see that there is a cylinder of light essentially, where because the object is at infinity. But if we are using a laser guide star, the laser is formed somewhere here in the Earth's atmosphere at a region of 90 kilometers from the 90 kilometers of elevation. So what happens is what we are sampling for detection will be a cone of starlight, and what we will be correcting for will be this whole cylinder of starlight. So we will not be, there will be some unsensed atmosphere between the cone and the cylinder, which we are not correcting for. So that is one of the things that is addressed by KAPA here. So you can see here that this is the residual turbulence, which is not illuminated by the sodium guide star, and we will, because we don't have any information about it, we are not able to correct for this. So most telescopes, what they do is they have two modes called the natural guide star mode and the laser guide star mode, where you switch to a laser guide star if the object of observation is below a certain intensity, is below a certain magnitude. Above a certain, if the guide star is faint enough, then you use a, if the sign star is faint enough, then you use a sodium guide star during that time. So this is the next level of AO system at the Keck I telescope, and this is the concept which we are using called laser tomography AO system. So here, what you can see is, instead of shooting a laser directly at the science object, there are laser tomography systems which shoot lasers on axis also. But in addition to that, we illuminate the region around the science object, usually a few arc seconds. In the case of KAPA, it's about 7.6 arc second around the science object. We illuminate the layer in a way so that we can see the edges which were not otherwise illuminated when we were using a single guide star. So in KAPA, we are not using a central guide star. We are illuminating with 4 guide stars around the central science object, and we are extrapolating the atmospheric turbulence in between using atmospheric statistics and modeling that we know of. Yes, yes. Yeah, it's not a point source. So the thing is, we do calibrations during the start of the night to compensate for that. The conversion between the centroids to the arc second, called the centroid gain. We do some calibrations during the start of the night by observing. It changes a little bit depending on the width of the sodium layer, but it's very minimal. So once we calibrate it at the start of the night, that conversion factor, then it's pretty much minimal, and we can use that for the whole night. It's just a conversion factor which we have to figure out, because we'll get different centroid to arc second gains for X and Y directions because of the elongation. Yes, yes. Yeah, so these are made by a company called Toptica currently, and so 589 nanometers sodium lasers, sodium wavelength. So whatever the sodium 2, I think, wavelength is, that is the wavelength which we use. And that is specifically used because for some lucky reason, we have this layer of sodium atoms waiting for us to be lased, where we can illuminate it and we can create an artificial guide star. There is, Yeah, so at about 90 kilometers above the Earth's surface, there is this very thin layer of sodium atoms, which is a byproduct of meteorites burning up and decomposing in the Earth's atmosphere. So I don't know the exact reason why they form at that layer, but that is the one that we use for creating the guides. So they are exciting the sodium atoms to the next energy layer, and when they come down, they lace essentially, right? They illuminate, and you can see as a star. You can see that an artificial, whatever magnitude you can see as a seeing limiter. You won't get a point source, but you will get an object of like 1 to 1.5 arc-second in size. No, it's a full filled Gaussian object. Yes. So during the start of the night, we get a list of areas in the sky which we are not allowed to point the laser at, sent from the Space Force, because they don't want us to illuminate satellites. So critical, spy satellites or something like that, which they don't want us to illuminate. And for the planes, actually, we have transponders. So earlier, what used to be done was 5 people used to stay at minus 20 degrees Celsius looking at the sky, very cold climates, not an enviable job at all. And you used to be press a big red button if you see a plane coming very close to the laser. But now we have transponders which directly communicate with the flight and automatically shut down the laser if the plane comes too close, and we get enough information that we don't lace in that direction. So yeah, so here, as you can see, you have multiple wavefront sensors for each of these laser guide star sources, and then you have one deformable mirror which is correcting for the direction of the sign star. So what happens is these wavefront sensors are looking in these directions, and they are not looking at the sign source. We combine all of this together. Instead of just one wavefront sensor to one deformable mirror, now you have multiple wavefront sensors creating the actuator output for one deformable mirror. And these actuator outputs are calculated in a way so that it is optimized in the direction of the science object, not in the direction of the laser guide stars. So that's how tomography works. You reconstruct the atmospheric turbulence information in between the guide stars and then optimize the correction for the central source. So, and there are multiple varieties of this. TMT, for example, is using this called the laser multi-conjugate adaptive optics system, where instead of just one DM, you use 2 DMs and the lasers are much farther apart. You get much lower Strel ratio at a much wider field of view in this case. So it depends on what kind of science that you want to do, whether you want to get direct imaging of exoplanets, high resolution imaging over small extended resolutions, or very wide fields you want to capture at mid-level Strel ratio. So depending on that, that's where it starts from. Depending on the science requirements, you decide the kind of AO system that you want to design. You cannot use one AO system for all players, of course. So this is the KAPA is primarily for galactic center science because it gives a high enough Strel ratio for an extended object of size like 10 arc-second or 20 arc-second size. And it gets poor much farther away from that. So there are 3 stages of upgrades which is happening in the Keck I telescope. And you can see this is the current Strel ratio as a function of wavelength, a science wavelength. And this is the RTC upgrade, which is currently happening, in the process of happening, where, as I said, it is addressing 2 major things, which is faster wavefront sensors a better computer to compute the wavefront sensing to correction faster, and in addition to a better camera, which has a better signal to noise ratio for the same magnitude of the guide star. So that will increase the STREL a little bit. And then now you add KAPA and TRIC. TRIC is, I won't be talking much about it. It's a infrared tip tilt sensor, which gives much better sky coverage for tip tilt sensing. But KAPA will add a much higher STREL at the wavelengths, as you can see, for the galactic center sources. So KAPA upgrade consists of all of this. This is already complete. It's called the laser upgrade. I think we had a dye laser, which was very expensive, prone to leakages, and was very expensive to maintain in terms of labor also. And that has been upgraded to a Toptica laser. This is at 22 watts, and it gives us enough power to split the laser into 4, so that we just using one laser. Lasers are expensive. Each of these Toptica lasers cost about $1 million, I think. So using one laser, we can split it into 4 and create 4 guide stars of magnitude of 7 or 8 on the night sky. So that upgrade is complete, was complete about 2 years back. And the RTC upgrade is the one which is currently going on, which I said is for the lower time delay error, where you can compute faster, have a better camera, all those things. And this is what I'm currently working on, which is the laser tomography, where you reduce the focal anisoplanatism and get better STREL while having a predictable magnitude for the guide stars. So this part I'm not much involved in. This is trick which I was talking about, and this daytime calibration platform goes hand in hand with laser tomography, because the correction, because the AO correction is a little more complex. As I said, you have to reconstruct the area between the lasers, and that is very model based. So, and the atmosphere is changing every day, and the model has to keep up with it. So because of that, we have to have this daytime calibration platform consisting of an artificial atmosphere, a controllable translation stages where we can actually test our algorithms before we can go on sky. So, yeah. So this, I'm not very aware of. I just put this slide just for information. I think primarily it's for galactic center science. It's for constraining dark matter, the Hubble constant, and dark energy. Yeah, I can read through it, but I'm not very aware of the science goals of this instrument. No. So KAPA will be installed on Keck I. Yeah. So Keck II is primarily for high contrast imaging. It has a pyramid wavefront sensor plus a fiber-fed spectrograph, where I think they're taking directly imaged exoplanets, where they can just get the spectrum of the planet just through a fiber. So that is the kind of science that they are working on. They're not working on any wide field adaptive optics system. So this is like a skeleton block diagram of KAPA, and the blue sections show the new additions that are added. This is the Asterism Generator. It's a bunch of optics which split the laser into 4, and it also consists of the uplink tip tilt mirrors, which actually control how the laser is launched into the sky. So even the uplink tip tilt mirrors have to be controlled at 1,000 times per second, not 1,000 times, about 100 to 200 times per second, because there will be a lot of changes because of the small flexures and changes in the way the telescope moves and how the sodium layer behaves. So there is a very active component inside this in addition to the optics which split the laser into 4 beams. And in addition to that, we have the wavefront sensor, the new wavefront sensor here. I'll be talking about it in the next few slides. And this is the low infrared tip tilt sensor. And this is the science camera called Osiris, science camera and spectrograph called Osiris. It's a fixed pattern, yeah. No, it's a fixed distance. So we did some modeling to estimate what kind of asterism would be giving the least amount of wavefront error and the least amount of model errors for the Keck seeing conditions. And we stuck with that. Otherwise, it's a little too complex, especially with the AO system have to track it very carefully. It's a little too complex to have different asterism sizes. I don't think it's planned to be like that in future. Yeah. Right? It's just fixed. Yeah. Yes. No. So this science instrument is also going to be upgraded called Liger. So it's an upgrade of Osiris. Again, I don't know much about it. Also a spectrograph and imager combination, which will, yeah, better in what ways. I don't know much about it. Yeah. Not by much. Yeah. Yeah. So what you do is you have a cylinder instead of a cone, so you basically compensate for the focal anisoplanatism.
What's the
It's like so the science instrument. So science instrument is around 20 by 20 arc seconds. A very small field of view. So anywhere within this, it's pretty uniform correction within this field of view. Like very close to the angular anisoplanatism. Or K sometimes in H, but J it's very hard to get. And so this is for Shivrani ma'am's question. This is the modeling that we did to figure out the 7.6 arc second at the different zenith angles. There were simulations to check what kind of asterism radius would give the least amount of wavefront error. So of course we cannot design for all zenith angles. So the sweet spot was found to be at 7.6 arc second, which would give the least amount of wavefront error as a median of all zenith angle combinations that Keck would be used. And this shows the asterism generator a little bit. So again, I've not worked on the asterism generator per se. So these are the tip tilt mirrors you can see, which actively control the laser's launch into the mesospheric sodium layer and make sure that it is keeping the 7.6 arc second asterism constant. So this is one major part which I've been working on. It's a wavefront sensor camera upgrade from CCD39, which is like the workhorse camera for all AO systems, fast wavefront sensor camera for all AO systems, mostly across the world, first generation AO systems all across the world. Even RoboAO uses the CCD39. But now, because of the laser tomographic adaptive optics and because we needed to have a much better measurement error, so we have bought this EMCCD, electron multiplying CCD. It has 240 by 240 pixels instead of the 80 by 80 pixels we have on the CCD39. And we have a pupil relay optics in the front of the CCD. It splits the light. So all the light from the lasers will be coming together into the telescope, and the pupil relay optics will be relaying the pupils into the 4 corners of the wavefront sensor. So instead of using multiple wavefront sensors, we are using the same wavefront sensor, but different parts of it. And we'll be, just instead of having physical boundaries, we are just taking region of interests in the four corners of the wavefront sensor, and we are computing tomography from that. So, but the problem is it's a very, very difficult camera to work with because it's very sensitive to over illumination. It's very sensitive to even shipping. We had one camera which got shipped where the capacitor of one filter tuning circuit changed a little bit, and it was having massive charge transfer efficiency issues. Even the characterization in the lab, it looks like a checkerboard pattern, as you can see, where it has multiple channels. It has 8 channels in total for the fast wavefront sensor readout. And the illumination between the channels can be very, very different, sometimes of the order of 3 or 4 times. Where you need very good flat fielding calibration, and maybe it may change over time. But the advantage of these EMCCD cameras is the readout noise. The readout noise is very small, 0.3 electron readout noise. So because of that, you get very high signal to noise ratio at low magnitudes. You can operate with much fainter guide stars. Because we are operating the wavefront sensor at very fast speeds, dark current, which is another major contributor, it's not usually a problem for wavefront sensor cameras. The readout noise is usually the main problem in wavefront sensor cameras, and this is injected by the amplifiers inside the CCD. So yeah, and we have installed this on the telescope, installed a camera on the telescope. We are actually installing this camera on both of the telescopes, one as part of KAPA and one as part of the high contrast imaging, and I'm characterizing both the cameras for both the telescopes. And yeah, so that's about it for the wavefront sensor. Yeah. Oh yeah, so sorry. So this one actually shows the illumination before flat fielding, where these are the fractions as compared to the maximum illumination. Let's say this is the maximum, this is the quadrant having the maximum illumination, and these are fractions compared to that. So if you put it at a gain of 1, which means that there is no amplification, there is no electron multiplication, it's a pretty decently behaving camera. But when you put a high voltage amplification, the noise increases by, the noise meaning the photon noise, there is a multiplication factor of √2 in addition to the usual square root of the signal factor that we are usually used to. And in addition to that, you get this checkerboard pattern where there is a huge variation between the quadrants. And this one is after flat fielding, the uniform image after flat fielding showing the noise which is remaining in the camera. So, and the noise which is measured as a standard deviation in each of the channels, the total noise in each of the channels. Yeah, so the gain increases. So what happens is the gain increases. We have to reduce the intensity with which we are testing the flat fielding, because otherwise it will over illuminate the camera, which means signal to noise ratio reduces that way. The noise increases that way. So that is one problem with these cameras, that we have to very, so one of the problems we are facing with implementation is suddenly if you are going by a cloud or something like that, the over illumination protection of this camera kicks in. So we ideally want to use it at this gain, the maximum gain of 600, where we get maximum signal to noise ratio with respect to readout noise. But when it is over illuminated, for protecting the camera, it jumps to 1. And then we have to do a set of sequences to get it back to 600, where we lose some time, so that has to be as soon as possible. And night sky time is very, very valuable. You don't have time to do these kind of things. So it has its advantages, but it's a difficult camera to work with. So now comes the tomography algorithm. I'll give a idea of how it compares a single LGS tomography versus single LGS AO system versus 4 LGS tomography. So as I said before, for a single LGS tomography, the sensing and correction is on axis. You just point the laser exactly in the direction of the science object, and you correct along that direction itself. And you have a closed loop AO reconstruction that I showed in the first slide. You just detect the residuals and you correct for the residuals as and when they come, as and when they change. And you have pretty empirical correction where what you do is you just poke the actuators, you observe how the centroids change in the wavefront sensor, and you create the matrix based on that. And that's pretty much enough for most telescopes. There are some polynomials which are usually added, but usually that interaction matrix, inverting that interaction matrix is enough for most telescopes. But for tomography, the problem is that the atmospheric turbulence statistics that we are used to, it observes the statistics called Kolmogorov statistics, and the residuals, the correction, so the wavefront which you get after the AO correction does not behave in a Kolmogorov statistics manner. So the problem with that is that you cannot insert your model. As I said, we have to use a model to figure out what is the atmospheric turbulence that we have missed in between. So for doing this, we have a model which works pretty well for open loop. Open loop meaning if we are reconstructing the turbulence, the entire turbulence, it works pretty well, but it doesn't work well for the residual turbulence that we have after correcting for most of the turbulence. So what we usually do is we have to combine, we have to add the previous turbulence, inject the previous turbulence to the residuals and create a fake open loop inside the real-time controller system. And this allows us to apply the model. I will be talking about that in the next slides. So this is how a pretty vanilla AO system works. A single laser AO system works where you have a pixel processor, where you have a flat fielding, background correction, all the things that you do to a camera. And then you compute the centroids, convert it into arcsecond of error, and subtract it by slope offsets. This is the, if you remember from the first slide, this is where the matrix multiplication happens, where you inject a set of slopes coming from the wavefront sensor, multiply it by this matrix, and you get a set of mirror disturbances or the mirror actuations. And you put it through a control system, a control log, and what you do is you do all the conditioning for the deformable mirror, ensure that it does not go over a certain actuator value, all those things, and you feed it to the D. So this is how a conventional AO system works. For a tomographic reconstructor, it's a little more complex. So as you can see, the new things which are added here are here. Here, as you can see, all these things are the same, how the camera pixels are conditioned, how the centroids are computed, that is the same. But then you see this thing where from the DM outputs, you condition the DM outputs to create what is called the pseudo open loop, where you add some parts of the DM output to create an open loop wavefront in this. So instead of multiplying with the residual slopes, here we have the residual slopes. Residual slopes mean whatever is remaining after the last time step of correction will only be visible here. And that is a multiplication which happens here. So instead of the residual slopes, here we have the residual slopes plus the slopes which have been converted back from the DM. And then we multiply it with a very special reconstructor called the tomographic reconstructor, which is very different from the reconstructor that you saw earlier. And that includes, this is a covariance matrix which includes the model of the atmosphere in between to point it at the science target. So we have to recompute this reconstructor every time there is a discernible change in the atmosphere, and where there is R0 values change, where there is layer seeing, different layer seeing values change, we have to recompute the reconstructor and then feed it into the real-time control system. Yeah, so this has been completely tested in lab. So as you can see, the matrices that are here are tiny when compared to here. You have multiple covariance matrices of the size of the actuators versus the wavefront sensors here, plus a lot more operations happening here. But the good thing is today's gaming GPUs are able to easily get this thing done without much effort. The computing part is very easy. We have a target of doing the real-time computation in each time step of 250 microsecond, and we are far below that number. We are easily able to get to less than 100 microsecond, which is 10 kilohertz of correction. So the limiting factor here is not the real-time control at all. So, and this is the more complex part of tomography, where in a telescope like Keck, night sky time is very expensive. So we want to make sure that we test the algorithms as much as possible during the daytime itself before going on sky. So yeah, so this is yeah. Yeah.
I think you had said that you have to keep the
7.6 arc seconds. Yeah.
Why does it change?
Which one?
Once you position it, should be remaining the same, right?
The telescope is moving, and so I mean there will be small flexure changes with gravity and the whole. So even the smallest of flexure changes in the small launch telescope we have seen just by a few arc seconds. So there should be active correction of.
It's sitting on the other side of the secondary.
Yes, yes.
Don't have something in you on top, so make sure that there is any additional load on the secondary.
Yes, yeah. So at that part, I don't know how they are compensating for it. But yeah, it's so we are not the laser is quite heavy, but we are not putting the laser on the back directly. So we are. Yeah, the beam splitters and the fold mirrors, but the uplink tip mirrors are a little heavy. Not very heavy as compared to the laser. These are small optics, but they are, yeah, they can add some weight to it. Yeah, they can flex when the telescope is moving and parking. So for the daytime tomography system, so in most of the telescopes which has an AO system, what you usually do is you have an artificial light source, usually a fiber-fed light source or a point source at the focus of the AO bench at one of the foci of the in the AO bench, which you can use in the daytime to calibrate for. Oh, okay. So this is the plane wavefront. These are the positions of the slope. These are the positions of the spots. If no aberrations are there, if no flexure is there. So under ideal conditions, what is the kind of wavefront that you get? So as I told you, because we have 4 lasers, that one light source has to be expanded to 4 light sources, first of all. So you have exactly the same kind of asterism that you have on sky on the AO bench also. The fiber-fed light sources at 7.6 arc second in the same wavelength of the laser guide star that you have, controllable in intensity and magnitude. And that is put here. So the light from the telescope comes here, and this side is the AO bench. So in between that, you have a set of translation stages with a fiber which can move in XYZ directions, which can position the light source for science camera, for the wavefront sensor camera, for the different sensors to calibrate the different sensors. So one of the overhauls has been to update upgrade the fiber to have a fiber bundle, to have the sine source and the 4 LGS and an off-axis natural guide star. And in addition to that, what we have is a telescope simulator. So a telescope simulator is, the function of the telescope simulator is twofold. Keck has the additional complexity that it's not a spherical monolithic, a circular monolithic mirror. So Keck is a very complex segmented mirror telescope. So if you inject a fiber source from here, the pupil is formed as a deformable mirror. The pupil is not reflected from the telescope mirror, which means that you don't get the edge effects or the issues that you normally would get with a segmented mirror telescope. So what we have here is a Keck pupil mask, which is very accurately reproduces the segments on a very microscopic level over there and creates the same beam, the F13.7 beam that is coming from the telescope. So the output of this is an F13.7 beam where the pupil is decided by this pupil mask, which mimics 36.5 millimeters. Even off-axis, if you consider, it's around 40 millimeters, including the 4 off-axis sources. So then we put, so in addition to that, what we have to simulate for is the finite height of the laser guide star also. So in the previous telescope simulator, there was one light source at equivalent to a conjugated altitude of infinity. But in this case, we are putting 4 LGS sources at 90 kilometer elevation, plus a natural guide star at infinity. So we can actually determine the errors due to tomography because we are actually injecting the tomographic error into the system. And in addition to this pupil mask, the focal anisoplanatism because of this finite altitude, we have, fast forward here, yeah, we have something called a phase screen, an atmospheric phase screen, which is manufactured by UCSC, Phil Hin's group at the Laboratory of Adaptive Optics at UCSC, which is a piece of glass where a coating is applied in such a way that it mimics the atmospheric turbulence characteristics very accurately on the glass. And what we do is we have this, we mount it on 2 translation stages. One translation stage is to adjust the elevation. So we can put this layer at different conjugate elevations, changing from 5 kilometers to 15 kilometers, as if the atmospheric turbulence is moving between these heights. And at the same time, we have a very fast translation stage, which can mimic wind speeds of 1 meter per second to 10 meter per second. So this cover like 95% of the wind speed cases at Keck. So as you can see here, this is the telescope simulator, and this is the source box, which I didn't explain. Sorry. So this is the source box which creates all the light sources, very, very ultra-stable light sources, which are fed into fibers and go into the telescope focus here and to the telescope simulator here. And we need both. So we are replicating this calibration sources 2 times because there are some advantages in just putting a calibration source in front of the AO system as opposed to the calibration source in front of a whole array of optics and the Keck pupil mask plus the phase screen. So the Keck pupil mask plus the phase screen is essentially used to ascertain the performance of the tomographic algorithms that we will be implementing to make sure that our models are correct. The other one, the standalone fibers, which are just in front of the AO system, those are just used for conventional calibrations in order to ascertain where the spots are, what is the wavefront that you will get, all those kind of things. That's a good question that we can that we still need to go on Skype. And it changes a lot. We did not put much effort into it because it's a very fast procedure during the start of the night to calibrate that. So this one, we can have several variations of calibrations depending on the signs that we are observing. Like sometimes we use a pinhole mask to make sure field distortions are not there among the science camera, non-common path aberrations. A lot of calibrations in the daytime that are more time consuming are done during the day. At the very end, go on sky, the first thing that you do is figure out the elongation, and usually it does not change over time, the elongation. I mean, I think they do it like once in a week or something like that. It's not a daily thing. Oh yeah, so we've just given old white light source. So we didn't want to retire the old white light source, so we gave some space for that also. So just in case, because as I said, if somebody wants to use distortion modeling on the science camera, it helps to have multiple sources and to have closed loop correction to see at the same time simultaneously what are the distortions at the different fields of view in the science camera. So yeah, and as you can see, you have different fiber bundles for AO bench. This is the one which is directly injected into the AO bench, and this is the one used in the telescope simulator. And the one used in the telescope simulator has slightly different spacing because it's at a different elevation, and the magnification associated with that to create a 7.6 arcsecond asterism is different. So these two have been installed. The telescope simulator is made in the lab. We are just waiting for the AO bench to be free so that we can install it on the telescope. So yeah. Oh, it's pretty small. It's around 125 millimeters by 100 millimeters. So that's what. So the pupil size is around 36.5 millimeters, right? So anything more than 40 millimeters, we don't need. So we split the phase screen into actually two parts because it's 100 millimeters in width. So the top 100 millimeters is coated. The bottom 100 millimeters is kept blank in order to do. So we can just push it to the light path and make sure that we are doing the right thing to just create a clear light path. Currently, because of the translation stage limits, we cannot have the phase screen out of the beam. It's a very small phase. Yeah, duration is also very limited. I mean, the duration is limited to 3 seconds at 10 meters per second. If it is slower, you can go for much larger durations. But at 1,000 frames per second, you get quite a bit of telemetry, 3,000 frames of telemetry for the adaptive optics system. So this is the setup that you can see on the lab where we are testing the telescope simulator with an Andor camera here, just to see ensure the asterism sizes are correct, the intensities are stable, all those kind of things. So that's about it. So I primarily worked on the daytime calibration part, and I am leading a team from Australian National University, Swinburne University, and Paris Observatory in creating the laser tomography system. So I'm contributing the algorithms from my side, and they are the ones who built the RTC, the real-time control system. So they are the ones who are incorporating the RTC according to our requirements into the Keck AO system. So, yep. Yeah. PLT Muse has Muse is there. Yeah, I don't know if it's operational or not. Gemini South is operational, right? Yeah, Muse is a huge instrument. It's a much bigger instrument than Jupiter.
I started just farming at 90 kilometers, right? So the wavefront coming from other stars, traveling much longer, and the atmosphere still exists above 90 kilometers.
Yes.
How does it limit the accuracy?
So that's a good question. So the thing is, most of the atmospheric turbulence is limited to the first 1 kilometer. In most of the locations, it's limited to the first 1 kilometer. It's called the ground layer turbulence. And there are, I mean, in good sites, the percentage of this reduces. There's still a lot of turbulence up to around 20 kilometers or so. But beyond that, the air thins so much that there's not much atmospheric distortion contribution beyond the 90 kilometers. For example, the alternative to the laser guide star is used in small telescopes. It's called the Rylai guide star. So it shoots a UV laser into the sky, and you just use the Rylai scattering of the particles, the back scattering from the particles till about 10 kilometers or so at 10 kilometers or so to observe the guide star. The problem is, as you see, it's a much shorter cone. You're not getting the atmosphere beyond 10 kilometers. That's why the most optimum technology that we have is this sodium laser, where you can create a star at a 90 kilometers.
That density is more important than turbulence. Turbulence should be more, right?
No. So the turbulence will not be more. So
if it's in thermosphere where ionosphere,
okay.
radiation is happening to the solar wind. So just thinking that not contribute wavefront deformation.
The optical distortion due to those high layers are very, very small. Maybe the optical wavelengths, the radio wavelengths, I guess, may be affected more by the ionosphere. I'm not very sure. Yes. So we use a one Karman. Yeah, one Karman. The outer scale is around 100 meters or something like that. Because it's a 10-meter telescope, we have to use an outer scale as we use larger and larger telescope. We cannot use an infinite. Yeah. So and one thing which I'm not sure of, I have asked this whether the outer scale does not change much over time, and you use a 100-meter one that has given us good performance in our. No, it's very difficult to.
This is a clarification.
That's what. So stars are much more brighter in the infrared than the visible. So you get a much higher sky coverage and less limiting magnitude in the infrared. So many telescopes around the world are shifting to infrared sensing. LGS, yes, exactly.
So in case of single guide,
yeah,
wavefront sensing is very good probably at the center of it.
Yeah.
So and if you have a very compact object,
yeah.
then both is something.
So what we usually do is we point the telescope in the direction where we want the maximum correction, right? So we put the science object in a way that it is at the center of the asterism, and then we compute the correction that is required for the on-axis. So we don't deliberately put it off-axis from the center, the science object from the sensor. But as you said, there could be what we are using is for the galactic center science. So there could be small variations in, there will be an off-axis, it will be an extended, there would be extended objects which we are observing, or even multiple objects which we are observing in the same field. And the whole point of the tomographic AO system is that you are adapting this for this kind of region. So instead of optimizing for the central on-axis, we can optimize for a larger area if need be by modulating the reconstructor and the covariance matrices a little bit. That's the advantage of it.
Daytime. So is it actually used in the daytime or?
So yeah, so I mean,
which parameter of the night you insert in the daytime?
So during the daytime, we have this atmospheric phase screen. Right? So the phase screen, I mean, it cannot simulate for all the atmospheric conditions of above morning AM. What it does is it takes the median scene. It has a set of parameters. The zero is where you want it used, and at different elevations, what is the percentage of seeing, fractional layer seeing which is there, and we incorporate that into the phase screen. So we use that as a measurement.
So then we use the previous night's information.
No. So we I mean, it's a piece of glass, right? It's a fixed piece of glass. So we use a median scene, but we have several phase screens which do like the 60th percentile of seeing, 80th percentile of seeing. So we will have an array of phase screen where we want to check, okay, in horrible conditions, and then
once you do this.
So what you do is, there is in tomographic AO, you tinker with the parameters a little bit to see, you get good correction on axis, you get correction over a larger field of view. So you may have to tinker with the parameters to check your models to see whether they are correct
On day-to-day basis.
Not on day-to-day basis. It's purely, as you said, it's purely like a few months exercise,
Okay.
and mostly it may not be used at all after that.
Once your system is trained, you don't get.
Yes. Huh? Jet stream.
You simulate it in daytime.
Yeah.
About by using the different camera, you're able to increase SNR. So is there any?
So it's like measurement error falls down a lot after like SNR of 5 or something.
SN5 and beyond, it is all.
Yeah, it depends on, yeah, exactly. So again, this is like a ballpark number that I'm throwing, but anything where you get photons which are of the order of like SNR of 5, or photon noise which is contributing to a SNR of 5 can be a problem. Photon noise plus readout noise. So in this case, for a magnitude of 7 or 8, which is a laser guide star, we will be 22-watt laser. So that's a good point. So it will be fixed for the LGS, but this will actually help in the NGS mode. We will still be using the NGS mode. So the NGS mode is still not depreciated or anything. So the RTC is trained to use with natural guide star mode, laser guide star mode, and the tomographic LGS mode. So all three, depending on the intensity of the target, let's say the intensity is sufficient enough for NGS, the first priority would always be NGS, because that gives the best trail as much as possible. Then the next one, if you have a little bit of field of view or like to get a better straddle than single LGS, you would use KAPA. And then for cases where KAPA cannot be used, let's say we have had, I think there are issues when we go close to like 60 degrees zenith angle or something, we'll use a single laser. So those are, yeah. Again, I'm not very aware of that section of the science case part of it. Natural guide star versus LGS is quite black and white. The bright star versus not bright stars, but you know, the tomographic versus the non-tomographic. It's the same frequency. It's like median is 1000 frames per second. So, but this RTC can go up to even 2000 frames per second. But it's not tested it at. It's always a you increase the speed, you reduce the number of photons coming to the wavefront sensor, you reduce accuracy of the wavefront sensing, but you reduce the speed to like 500 or 250 or anything, and you're not tracking the atmosphere as fast. So if it is bright enough, we can go much faster. So, yes, exactly. So the advantage of tip tilt is that it doesn't have to be at this high intensity as the high order correction. So the high order correction, the problem is it's split into multiple places, and this one you just take the image on a camera. So the whole starlight comes on a camera, and you just check 4 pixels. It's like a quad cell where you just see how it is jumping around among 4 pixels, and you can determine the tip tilt. Yeah, something like that. No. So we use a separate. So that's the one I showed. Yeah. In addition to the infrared, we have a visible also, which is. Yeah. Yes. Yeah. If you're using a natural guide star AO, you use the tip tilt information from the natural guide star itself. Yes. Yes. No. We don't. So the tip tilt sensor is only for laser guide star. Yeah. So otherwise, what you do is you actually extract the tip tilt information because it's included in it. The problem with LGS is the double path problem, right, where you cannot detect the tip tilt from the laser guide stars.
So you have 4 wavefront sensing.
Yeah. So that's one thing we solved with a single camera, right? So we are using a single camera for all 4 lasers. So we are reading all of them out at the same time, and
single laser as well as single camera.
Yeah, single laser is split into 4 and using a single camera for one.
So thanks, Avinash, for giving this briefing. If you have any questions, you can write to him. And seminar, I think, today, but I think next week or so, 26. Please join for that as well. Thank you.